So this is the first lecture on Chapter 8 where I try to summarize the material in Section 1 and Section 2. So Chapter 8 is on solutions. A solution we did talk about before when we talked about matter. There are pure substances and mixtures. Mixtures can be heterogeneous or homogeneous, and a solution is a homogeneous mixture. It's uniformly mixed throughout, even down to the microscopic level, so it does not look cloudy. It looks clear, and there's no chunks or droplets or anything uneven about the mixing. Two other definitions: the solute is the compound being dissolved, and the solvent, present in greater amount, is what the solute is dissolved in. So for a mixture of sugar and water together in a cup, when you mix them, which is the solute and which is the solvent? The solvent would be water, and the solute dissolving in the water would be sugar. So that is what we typically think of when we think of a solution. We think of a solid like sugar dissolved in water, but there are other solutions that you can have. You can have a solution of gases. The air that we breathe is a solution, evenly mixed, of oxygen and other trace gases, which are the solutes dissolved in nitrogen. Nitrogen, since it's present in the greatest amount, would be the solvent in that mixture. Also, you can have a solution that is a solid. Metal alloys are solutions. So if you melt a couple of metals and then evenly mix them throughout, then even when they solidify again, they are solutions. For example, brass is a solution of zinc, the solute, which is present in a smaller amount, dissolved in copper. Copper is the solvent because it's present in a greater amount. When you're trying to figure out whether something will dissolve in a solvent, remember the rule that like dissolves like. So polar solvents, such as water, are better at dissolving polar compounds or ionic compounds, but they are not as good at dissolving nonpolar solutes, like gasoline or oils, things like that. Nonpolar solvents, on the other hand, would be better at dissolving those nonpolar solutes, but they would not be good at dissolving polar compounds or ionic compounds. Water is the most common solvent that we talk about. Remember, water is very polar. It's even capable of forming hydrogen bonds because it has OH groups, so that's an extreme form of polarity in a molecule. The molecule has a partly positive end and a partly negative end, so that helps it handle ions floating around in solution when it dissolves ionic compounds, salts. Your text on page 302 has pictures of the positive end of water surrounding a negative ion or the negative end of water surrounding a positive cation. So most of the solutions we talk about will be aqueous, which means that it has water as a solvent. And if you do see a bottle in lab that doesn't say what the solvent is, for example, it might say 2 molar hydrochloric acid, then the solvent is understood to be water. Electrolytes are compounds that dissociate into ions when they dissolve. So ionic compounds, in other words salts, are strong electrolytes. They completely become ions when they dissolve in water. A non-electrolyte, most covalent compounds, whether they're polar or nonpolar, are non-electrolytes, and so when the compound dissolves in water, the molecules separate from each other, but each molecule stays together as a neutral molecule without a charge. So there are no ions. A weak electrolyte is a little bit in between. Some polar covalent compounds, especially weak acids or weak bases, mostly stay as molecules, but there's a very, very small percentage that dissociate into ions. And so there is a small amount of ions in solution, and that's a weak electrolyte. If you have a solution of strong electrolyte where everything is dissociated into ions, that solution will conduct electricity very well. A solution of a weak electrolyte conducts electricity weakly, much more poorly, because it has a much, much smaller number of ions floating around. Most of the things in the solution are neutral molecules. In a solution of a non-electrolyte, all the things that are floating around are neutral molecules, and so there are no ions and it does not conduct electricity very well. So there's a picture of a light bulb being connected through these different kinds of solutions in your textbook on page 304, and you can see that the strong electrolyte conducts electricity well, whereas the other solutions not as much. So ions have different charges, and we can refer to the amount of charge that's in a solution as an equivalent. When we talk about an equivalent, then one equivalent means 1 mole of charge. So for example, 1 mole of sodium plus 1 has 1 equivalent of charge. Each sodium atom is plus 1, and a mole of sodium gives you a mole of positive charge, 1 equivalent of positive charge. However, a mole of iron plus 3, has 3 equivalents of charge, because each iron atom has a positive 3 charge. So 1 mole of iron atoms has 3 moles of positive charge, 3 equivalents of positive charge. Of course, we can't just have the sodium and the iron in solution, because we would have to have an equal number of negative equivalents of negative charge to balance it out, because the solution overall has to be neutral so the electricity doesn't start shooting out or something. Also, one more point to make is that a mole is a lot, so a solution with an equivalent of charge in it has a lot of electrolytes. That's more than we would use in, say, a medical application like an IV bag or something. So a lot of times the term milliequivalents is used because that's smaller, more realistic. And just to remind you, one equivalent would be 1,000 milliequivalents. 1 milliequivalent would be 0.001 equivalents, so the same metric prefix. And your textbook on page 307 has an example of a typical solution that you might find in a medical setting. So here are some slides where we can check the understanding of what we've just been talking about. You would have to pause the video to wait for the answer, because I'm just going to go ahead and record it. So which compounds would dissolve well in water? We have a few examples of different compounds here. All right, so if you've taken some time to think about this, let's go ahead and point out that bromine, the first compound, is a nonpolar covalent compound. The bromine atoms share the electrons equally, so it's a nonpolar bond between them, and that would not dissolve very well in water, which is a polar solvent. However, hydrochloric acid is a polar covalent compound. The hydrogen and chlorine share electrons unevenly. The molecule is polar, and so it does dissolve well in water. Sodium nitrate is ionic, and so that dissolves well in water. However, C3H8 propane is a nonpolar covalent compound. Carbon and hydrogen share electrons fairly evenly, and so those are nonpolar bonds and a nonpolar molecule that does not dissolve in water. Carbon tetrachloride, the bonds are polar, but the molecule overall is nonpolar because the dipoles cancel each other out. They're arranged symmetrically around the carbon, so that nonpolar compound would not dissolve in water. Potassium fluoride is ionic. It would dissolve in water. Acetic acid and glucose, shown on the bottom, are very polar compounds. They have OH groups on them, and so they're capable of hydrogen bonding. And so these extremely polar molecules would dissolve well in water. On this next slide, I've removed the substances that would not dissolve in water. So these ones that are left, if they did dissolve, would the solutions conduct electricity? I wanted to point out that hydrochloric acid, since we have not covered acids yet, hydrochloric acid is known as a strong acid. So when it dissolves in water, it completely dissociates. All right, so if you've had a chance to think about this a little bit, we'll move on. And hydrochloric acid, since it completely dissociates into ions in solution, that's a strong electrolyte. The other two compounds, sodium nitrate and potassium fluoride, also completely dissociate when they dissolve in water, so they are completely ions in solution, and those are strong electrolytes. They would conduct electricity. Acetic acid is a weak acid, so most of it stays as molecules in solution. Only a very, very small percentage dissociates into ions, so it would conduct electricity a little bit. And glucose would stay together as neutral molecules. It's a non-electrolyte, does not dissociate, and would not conduct electricity. And so here is a check on our understanding of the term equivalence. How many equivalents of charge would be in a solution that has 2 moles of sodium chloride in it? Or how many equivalents of charge are in a solution that has 1 mole of zinc sulfate dissolved in it? So in the first example, 2 moles of sodium chloride when it dissolves gives 2 moles of sodium plus 1 and 2 moles of chloride minus 1. So that would give 2 equivalents of positive charge from the sodium and 2 equivalents of negative charge from the chloride. Altogether, that would be 4 equivalents of charge in solution. For the zinc sulfate, we have 1 mole of zinc plus 2 ions, so that gives 2 equivalents of positive charge. There are 2 moles worth of positive charge from the zinc plus 2 ions. And in the same way, the sulfate with a minus 2 charge, 1 mole of sulfate would give 2 equivalents of negative charge. So 2 equivalents of positive charge from the zinc and 2 equivalents of negative charge from the sulfate would give 4 equivalents overall in that solution.